Yes.
Mr. Chai is here. Chai Zhou, is it the first person? It's not here yet. Chen Huan Eng.
Yes, I'm here. And Miss Chai Xiaowei type yes in the chat.
All right, okay. So Chong Ji Jian.
Yes.
Chong Jian Yan.
Yes.
Chua Ka Sing. Probably not in yet. Chua Yi Heng. Desmond Lee.
Yes.
Desmond.
Yes. Yes.
Paris. Already I saw you.
Yes.
Dan.
Yes.
Garrick. Henry.
Yes.
Garrick's not in. So if I address you wrong, please tell me if I get it wrong. Yik Hao.
Yes.
Guan Ting. Li Haoyuan.
Yes.
Li Hongyi.
Yes. Yes.
Li Yonghao.
Yong-Hao, he withdrawn already.
All right, okay, yeah, okay. This is the mechatronics group. So to go back, Ali Guan Ting, are you here? Have you applied? Nothing? Derek? Kasing?
Yes, I'm here.
Who are you? Please tell me your name. You who responded yet? Yeah, the name? So Kasing, are you here? Next person, Lee Yong-Hao.
Lee Yong-Hao, he withdrawn.
Sorry, yeah, I know that. I'm sorry. Lim Jin-han.
Here.
Yu Jun-jie.
Here.
Lo Siu-lun.
Yes.
Ying Pang.
Here.
Cafe. Ngo, I saw you. Chun Hub.
Here.
Good.
Here.
Jun Yuan.
Yes. Yes.
Dave. How should I address you? How does your friend address you here? Is it Dave or?
Yeah. I'm Dave.
All right, fine. Raymond.
Yes, I'm here.
Junang. Q Pink. Mr. Wong, are you here? Li Chen. Wong Manson.
Here.
All right, good. Xing Wei.
Here.
All right, so going back to the list here, Wong Li Chen, are you here? Wong Q Pink, Tam Jun Ming.
I'm here.
Yes.
Who's here? Tam Jun Ming, is it?
Yes.
Shipping.
Shipping is here, all right, fine. All right, Cafe? Nope, okay. So we have, who else? Guan Ting, have you arrived? Derek.
Yes, I'm
And
here.
Derek, you're here, fine.
Yes.
Kasing?
Yeah, I'm here.
Try Kasing, huh? All right. Well, I don't do this always here. So this is the first time. I just need to know your name, and that's why I'm calling one by one here. So in future, this is not going to be the way to take attendance here. Is that clear? So meanwhile, you can off your camera. Thank you for turning on here. You can hear me loud and clear. All right. So turn off your camera. Thank you. So let's start. The class now. All right, so the paper that you're sitting for here is a 4-credit paper, 4-credit hours paper here. The name is Engineering Materials. So basically, you can see this is C as in common among mechatronics and materials. Mechatronics and mechanical engineering students here, who are all from mechanical department. So you can address me as Ms. Ng. This is my email. You can always find me through the email. So I'm seeing you today for lecture 11 to 1 Tuesday, 5 to 6 Thursday. So this is a 3 hours lecture paper, and that's why it's 4 credit hours. It's quite heavy. So I've seen one group yesterday for a lab session. I believe the mechanical group has
Miss.
seen. Yes.
I haven't signed the attendance.
Yeah. I'll do that later. Wait, hang on there. Anyone here?
Okay.
Wait. What's your name?
Wang Li Qian.
Anyone else here? Cafe?
Thank you, Miss.
Cafe, welcome. Cafe not here yet. One thing. All right, we shall come to that later. So going back to the scene, are you at the PowerPoint slide here? Are you guys seeing the PowerPoint slide at the moment?
Yes, yes.
All right, fine. So now where am I? Okay. So how's the lab session yesterday? The mechanical group. Any feedback? The group that went off with Dr. Ho at 10.
Yeah. Yesterday was okay.
Yesterday was fine. Then the other group, the other group is the mechatronics group with Dr. Ng in the afternoon here. How was it? I think this group let's look at that. Is it A5 A5 or A6? Mechatronics students?
Yeah, okay.
Okay, it's okay.
You sure?
Huh?
You sure?
Yeah, okay.
So you understood clearly the briefing, huh?
Yeah.
Okay, all right. So let's go to here. So I'm going to see 3 other groups tomorrow, and Thursday and Friday. So the thing here now is because it's MCO, so you don't get to see us face to face here. All right. So the way the lab is going to be done is briefly explained by each of the respective lecturers, as in the grouping yesterday. All right. So you can find Dr. Ng. This is her email. You can find Dr. Ho. This is her email here. All right. So please make sure you guys and girls meet the deadline to submit the lab report on time, because there will be penalty. Is it clear? All right. So I see that the holidays on Thursday and Tuesday along the month of July and August here. So replacement will happen later. Is it clear? So next one, this paper here, as I said to you, it is a 4 credit hours paper here. So what you have basically it is a paper on materials sciences and linking that to engineering application. So these are the learning outcome. You can actually relate the learning outcome here. Now, very important, when you come to every single subject that you have in this semester, you look at the Bloom's taxonomy. So the Bloom's level here is C3. C3 means application. 3 is a level of application here. So whatever question that you see will be applied as in concept and principle behind it. All right. So we have 3 main learning outcome. The 4th one is onto the lab practical session here. So you can see the list of experiment in the lab session is packed to the course learning outcome number 4. And therefore you will have most of the focus on heat treatment. And of course, upon heat treatment, you have to have a change in the strength of the materials, which goes into the changes in the microstructure of the samples. All right. So the most important thing that you're going to cover in this paper is about structures and mechanical strength of all materials, range of materials that is available, as in polymer, metals, composites, you name it, all range of materials. So heat treatment is important. It's a way to change the structures of the sample that you have in hand, and therefore enhance the strength or decrease the strength here. And in interpreting this heat treatment, how does it work, the mechanics behind it, you have to understand phase diagram. So my questions in the final exam will be based on a learning outcome. So the way it is set here is applied to the learning outcome here as well. So this is the assessment mode. Basically, you have a 2 hours written examination online, which make up of 50%. The 2 hours written exam here are done in such a way that you have to answer 4 questions, 25 marks per question, add up to 100. So that 100% written paper contributes only 50% to the final marks. The other final marks of 50 come from your coursework. So your coursework, as you've seen in your lab practical, there are 6 experiments. You shall have the experiment 5 and 6 lab report merged as one, because the similarities behind the heat treatment concept for the lab 5 and 6. So this goes to portion of it, 50% from the lab reports. Another portion will come from your group assignment. Are you clear? So the group assignment here is going to be a group, as it is implied. So probably it's about 3 to 4 in a group. Of course, the structures of the assignment here will be given to you later. So in order to pass this paper here, you need to have a 50% of the coursework, which is marked per 100, and a 40% of the written exam, which is marked per 100. So add up to here, you must get the C minimum as a pass here. Now these are the lab schedule. This is given to you in the syllabus as well. Extract it from there. So you can see the lab session here, each has 4 hours of contact hours. So basically it runs for 2 weeks. So this was week 1, we are going to have a safety briefing, which should be done in 2 hours. So if there's anything that you are not sure of, you got to ask. Do not keep quiet. As I told the group yesterday, I am not psychic. I can't read your mind. So I always welcome two-way communication. All right, and then this will run for every 4 hours of the lab session in a weekly basis here of twice it's going to be running for 4 hours for each experiment here, leading up to the last of it, which is on week 13. The following this, it will be a final recap and feedback from the marks that you have gained and the performance of the paper. So the syllabus here basically covers as in first lecture you're seeing here is atomic structures. It's a little bit on the chemistry. It's sort of like walk down the memory lane to recap back the bonding that you have learned in Form 4, Form 5, the SPM level here, and apply that into the a range of materials. We shall see into that. So next one, we will talk about structures of materials. Basically, emphasis is onto metals. All right, and applying this to phase diagrams to illustrate phases available to predict structures and properties. At the same time here, when this happen here, the grain sizes have changed and also the phase distribution as well. So lecture 3 will involve dislocation and point defects on plastic flow in metals. Lecture 4, which is the heat treatment, part of the learning outcome, CLO number 2 and 3, apply to the range of metals. Heat treatment is most likely onto metals. Very rare you have it onto a polymer or plastics here. Next one, you have electrical properties of smart materials, semiconductors. All right, so this will be one of the range that you're going to cover. And lastly, we talk about properties and typical application of each group of materials in engineering field here. So the highlight will be ceramics and composites, because the metals are being explained in the earlier part of heat treatment. All right, any questions so far? Okay, so the books that you have, yes?
For the written exam, we do in a Google document.
That one has yet to be it will be announced later.
Oh, okay.
Yeah, announcement will be made later. All right. So next one here. Thank you for your question. So the next one that you have here, reading text here. So I understand that you're now all at home. You may have no access to the physical library building in the campus, but you can have ebooks. So grab hold of this ebook online from Callister. It's a Bible. If you go everywhere in the world here, United States, Australia, UK, people are using this book. It's a Bible here. Smith is also another Bible. These two books are pretty good. The way it's explained is quite detailed, and the wordings are quite simple, straight to the point. And our students here, you can use them, but it's a little bit advanced, as in the way the construction of the contents here. So if you can get hold of any of these 3 books, it will be fine. So let's look at the lecture. Now, before I go to the lecture, let me show you something. All right, can you see the lab? Can you see my Word document?
Yes.
Yes, all right, okay. So this is guidelines to write your lab. I believe Dr. Ho has done this. All right, I believe Dr. Ho, Dr. Eng has done this. They have explained to you guide to writing a laboratory report. Am I right? Can someone give me feedback from Monday class? Okay.
Yes.
No.
Yes.
Yes.
None for mechanical.
None for mechanical. Never mind. All this will be in the classroom. All right. So the guideline to write a report, as in similar to what you have done in the first year. This is a technical report here. So similarity on the scope of the content is somewhere along the line here. All right. Now, one thing I want to highlight to you guys to writing your report. So in your report, let's look at your lab session. Did Dr. Ho or Dr. Ng show you this lab schedule?
Yes.
All right, for both mechanical and mechatronics. So there are 5 reports to hand in here, as I said to you, but 6 experiments. So the lab 5, which is this and this, is going to be merged as one report here. All right, so we have 5 reports to hand in. So the 5 reports to hand in here comes to the marking rubric that you have here. So is this explained as well in Dr. Ng and Dr. Ho's briefing? Theory
Yes.
class? Good, brilliant. All right. So the aim, yeah, very good. Thank you. The aim is to score 5, rating 5. Of course, you can, if you score rating 5, it'll be wonderful, fabulous. All right. So basically, what you have here, follow strictly the marking rubric. We call it marking. We call this marking rubric here. So to score 100 marks, add up together is all 100. 20, 35, 30, 15, 100. Each report is marked per 100. So add up to it will be 5 reports, and then that goes to only 25% of the raw final marks here, because another 25% will come from your group assignment. Am I right? Okay. So I hope this is clear. So look at the rating here. So you won't want to go to rating 1. Everyone aim for 4 or 5, the highest of that. So basically, read thoroughly what is the expectation, and then from there you go to write your report based on respective experiment that you are running for that particular week. Week 2 you run experiment, and then week 3 you will have questions behind the experiment sheet to answer. All right, and that goes to here. That's why the problem and questions is 35 marks here. It's quite extensive. Is that clear? So answering questions, well, we all know questions comes with answers that are not fabricated. So your answer is going to be authentic, original, and there's no cut and paste here. So try your best to write as in your own wordings. You may have reference. So referencing are very important. All right, your friends has informed me the way they have done it previously. So today I'm telling you referencing is superly important. So referencing, as in what do you mean by referencing, is that you need to have a reference text as in the form of physical hard paperback book or e-books or publication of journals, conferencing, or any kind of valid journals that is available in your hand. So let's talk about referencing. This is 20 marks. I give such high rating to this 20 marks here because it's 5 times 20. So it's that you must present an accurate summary of your work done here. So the work done here must reflect how much effort you have put in, of course, along the way, the time that you have spent. So when talking about referencing here, this how referencing is very crucial, very critical. You do not write anyhow you like here. It's no fancy whimsy way here. So how referencing this document is in the university website. You go to the student intranet, you should be able to get this copy here. So follow strictly if you're using media, let's say YouTube or video. If you're using a physical hard paper book, how do you cite them? If you're using ebook, if you're using someone's quotes, all right, etc., etc. Here. So all this must be understood and well presented. So make sure you have this in hand. You read through it. All right. The same applies to my assignment. So my assignment will need referencing as well. A large portion of marks is allocated for that. So when I say referencing here, number one, Wikipedia is banned. Do not use Wikipedia. All right, and do not use anyone's blog. Do not use google.com. Don't give me search engine. Do not use my lecture notes, Miss Ng's lecture notes, Miss Ng lab manual. No, these are not allowed. All right, use original, authentic website here. And sometimes I do expect you to like every single website that you visited, there is a webmaster. So sometimes you may need to have access to get permission from the webmaster to quote their references as being used in your write-up here. Is that clear? Any question? All right, so this is guide to a writing report, and referencing is explained to you. Marks is being explained along the way during your lab session here. So let's go to the part I want to highlight to you. So when you write your report, you have illustrations, diagrams, charts, statistical data, and those are presented in the way of a table or in a way of diagrams here. So make sure when you write it as a diagram, the figure, the caption is always at the bottom of the diagram. If it's a table to illustrate a certain charts, a certain statistical data, a certain standards, let's say American standard of a testing method here. So the table must be with the caption here on top of the table. All right, follow? Okay. So next one here I want to highlight to you is that this is the syllabus I've really uploaded to the classroom. So make sure you read through the syllabus here. Follow strictly the scope. You can see the hours here is 3 for this lecture 1 and etc. etc. So everything is quite clear cut. If you're not sure, you email me and ask me. All right. Any questions so far? Oh, so much chat here. All right. So can you hear me?
Yes, we can hear you.
You hear me? Yeah. All right. Okay. Anything, you just pause me here. All right. Thank you.
Miss, I have a question.
Yes. Yes.
The lecture notes that you posted is just for chapter 1.
Yes. Correct. Exactly. Yeah.
Is it possible that you post every chapter out first, because I need to print it out so that I can do notes on the paper?
Yeah. All right. Understood. Yes. It's the first lecture. That's why
Okay, thank
I put one on. Yeah. All right.
you. Okay.
The rest will come in today here. I put in one on it. Okay. Any more question to ask? Yeah. As I said, yes. That's one. No. All right. So let's go on here. All right, let's start the lecture. So all right, so the first lecture that you have here, according to the syllabus, is me read back the thing there. Okay, materials classification. So these are the scope that you're going to cover for this lecture today. It looks something similar to your chemistry paper, but it's not exactly everything. All right, so let's look at first thing first, classification of materials. So I will ask question along the way. So when I call your name, just respond. Nothing critical. All right. So the first materials that you see in here is metals. So example of metals, you have precious metals, for example, the gold, the platinum, the silver. Of course, the more common metals here are the iron and copper and aluminum. So these metals are important because normally you will see them being combined with non-metallic element, and that goes to forming ionic compound. So non-metallic element here comes from the group 4, 5, 6, and 7. The 8 is in a group in the periodic table. All right. So basically, metals are very important, and they are actually recyclable. And the properties that they have here, we all know they have good thermal and electrical conductors here. So two category of metals that you have. Metals is pure single atom. When you have alloy, it's a combination of two metals or more, meaning a mixture of two metals and more. The purpose of mixing them is to enhance the strength here. So you can categorize metals and alloys to one, ferrous material, two, non-ferrous. Ferrous means anything that have iron, Fe, which comprises steel and cast iron. Non-ferrous means anything that doesn't have iron, the copper, aluminium, the molybdenum, you name it, all from the non-Fe based iron, Fe based metal here. All right, next one is polymer. So polymer is what you always use every single day, and it's a big issue to pollution of the Mother Nature here. So polymer in here is plastics, as in particular. We're talking about this range of materials. So the one that you always have seen before is a PVC or polyester, and basically everything you touch nowadays are from plastics. All right. So next one, you have ceramics. Ceramics, the common ceramics that you have seen in your house is probably the tiles on your floor, on your ground. And the ceramics that we're talking about here is more to ceramics as into engineering application. All right, we use one of them into the furnace lining, the fuselage in the space shuttle of the aerospace shuttle here, or even the so-called aeroplane. Sometimes they use ceramics materials. The turbine will need to be pretty hard. Okay, so this is one of the range that you have here. Glasses is also ceramics, and also silicon nitride. So the next one you have is composites. So-called composites, the common material that you see is basically your badminton racket. It is made from composites, your tennis rackets as well. All right, composites are super materials. They are pretty light, and at the same time here they have the strength that you need to enhance its wearability here. All right, so next one you have a range of electronic materials. So the IC, which is integrated circuits, most of them you can know that they are made from silicon. All right, so this is one range of materials. We will talk about that later in one single topic on its own. All right, so to start with this category classification of materials here, we have to understand what exactly are materials. So every single material that you see or you touch, it is made from the so-called atoms of certain elements in the periodic table. So firstly, you need to understand the structure of an atom. I think this is a recap of your chemistry. So nothing will be touched on this scope here. All right. So first thing first, you have the Z atomic number, which is the proton number. Then you have the A, which is the mass number, or we call it atomic mass here. It's made out of neutron plus proton. All right, N plus P. So what you have here, this way to illustrate elements in the periodic table is shown in your chart of the periodic table clearly. So in seeing this here, A and Z is important because it reflects to you. If you're talking about a neutral atom, let's say for example a neutral atom of an element aluminium, Al. So aluminium has how many electrons? Anyone? Any idea? Do you know how many electrons does aluminium has? So let's go back to your let's go back to your periodic table. Can you see this periodic table? Okay, so this is your periodic table. It's pretty small. So we have your periodic table here, group 1, group 2, then we have 3, 4, 5, 6, 7, and 8 here. All right, so we're talking about aluminium now. Aluminium here is number 13. Number 13 means the atomic number is 13, proton number is 13. All right, to have a neutral atom of aluminium, you have 13 electrons as well. All right, so the thing here is that we're talking about aluminium as in a metal, so it is a conductor. So when we say aluminium has 13 electrons, we need to know how are they represented. So therefore, you have the structure of the atoms. All right. So when you structures of the atom here, all right. So structure of atoms is something not new to you. You've learned it in Form 5. Your Form 5 teacher will probably tell you, well, this is how you draw a structure in a circular orbits. All right. Basically, this is just a schematic level. All right. So what you have in the center is nucleus. Nucleus is where you have the protons gathered together, and therefore it gives the charge of the nucleus, which is positive. And at the same time, you also find in the nucleus here there are neutrons. All right, and surrounding the nucleus is where you see electrons are being placed, and Form 5 level they call it orbital or shell. All right, so each of the shell here you are supposed to have a certain number of electrons. So the electrons here is bound by formula to obey that you cannot have more or less more than a certain number of electrons within a certain shell here. So this is the concept that you learn in Form 5. So this is called Bohr's atom here. All right, Bohr's has a higher level of explanation onto the atomic structure that you have learned in Form 5. So you can see from here, basically, can you tell me what element is this? Anyone? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is element number 12. If you look at number 12 here, is magnesium. All right, so magnesium here, look at the periodic table in your hand here. So magnesium here, you can see in your Form 5, your teacher will tell you this is your valence electron at the outermost shell, which is what? 2 electrons here, which means that the so-called magnesium is placed in group 2. All right, and from here, this way of explanation doesn't fulfill some of the observation from the properties of materials. So there must be a better way to explain it on how do we find electrons and how do they play a role in the metals or the alloys or the polymers or the ceramics that you have here. All right, so in here, let's look at how do we enhance the role played by electrons. So to recap back, so an atom is what you learn in Form 5, smallest particle of an element. In this atom here, we have the nucleus, whereby in the nucleus, you have the proton and the neutron in the same region. And the number of proton here will deduce the number of electrons as in having the same number because they are neutral. All right, so atomic mass, which is A, is the number of proton and neutrons. So this is the way you write your symbol for your element. So X is your element, all right? So your A is at the bottom, your Z is at the top there. Sometimes some references they use the other way around, A as in here, Z as in here. It's not wrong as well here. All right. So all the while here, I've been talking about the states of charges as being neutral because the number of electrons and protons are the same here. All right. So unless you do something to the number of electrons, you either remove them or you give them more electrons here. So therefore, you have charges. More electrons means they are more negative. Therefore, they are anion. If you take away electrons, means there are less electrons, and therefore the number of protons is positively charged here. So therefore, there are more positive here, and this is called cation. I think this is quite common. You are aware of this. Right? In saying this here, we go to one concept, which is isotope. So isotopes are referring to atoms of an element having the same number of protons but different number of neutrons. A very good example is your hydrogen. We have the protium, deuterium, and tritium. All right. So hydrogen is special. 1 1. You see hydrogen? Do you know what is missing in hydrogen here? Anyone? Henry Teo, do you know what's missing in hydrogen for protium? For protium hydrogen? Henry, are you here?
My chemistry is not
Henry?
good.
Do you know what's missing here? In protium. Relax, it's only first lecture. In protium, what's missing here? It has no neutron.
Yeah.
Right? There's no neutron here. So hydrogen is a very special element here. Very special guy. Okay, so deuterium and tritium here you can see is the radioisotopes of the hydrogen here, and therefore they are not stable. All right. So another example of isotopes is your carbon. You know your carbon-14. The carbon-14 is used for dating. Yeah, it's not that kind of dating. Dating referring to the carbon-14 is being a radioisotope here, so you can actually deduce how old a certain artifact is being dig out from the ground, and then you can do some study on it here, right, based on the carbon dating. So the normal carbon that you have is carbon 12, which is number 12, as in carbon has being the element number 6. Yes, 6 proton and 6 neutron and 6 electron. That's why it's 12. 6 plus 6 is 12. All right. So let's look at the role played by electrons. So electron is very important because I'm teaching this chapter here. So as I said to you, it's something like chemistry, but it's not exactly chemistry. So let's look at the electron role here. So electron is not able to be explained if you talk about what you have seen in your form 5. It cannot explain some concept of why certain behavior of the element is illustrated. Right, so what you have here, this comes into quantum mechanics. So quantum mechanics here is talking about the sense that a particle, in particular here is the electron, it behaves like a wave and it behaves like a particle. This is called duality. That means it's something like what do you call it? Two characters in one person here. All right, so the electrons as well here, it is having this so-called two what do you call it? Two behavior. All right, one being a wave. All right, two being a particle. So when I say particle, what do you mean by particle? Particle means they have mass. Mass means if the if the electron has mass here, and we all know that electrons are not stationary. It's always revolving around the nucleus, which is positively charged within the region of the orbital that is confined to it. As what your teacher told you, this is the shell. All right. So what you have here, basically, when anything moves, there will be kinetic energy. When anything moves, there will be potential energy because of this position of the point A moving to point B here. So there are energies allocated to this electron here. So this electron here, it has mass and it has energy, and therefore it must follow the concept of momentum. So momentum is mv. You learned that in first year, correct? Mv. So momentum is mv. M referring to mass, and the v refers to velocity. All right. So therefore, it explains the electron being a particle. So next one, we all know that electrons also behave as a wave here. So your wave here is illustrated as in the principle of wave, as in one electron can be diffracted, interfere, reflected, and refraction. All right, so these are the four properties of wave here. It is exhibited by all, whether you're talking about mechanical wave, water wave, thermal wave, it is all exhibiting these properties here. All right, so you can see from here, electrons behave like a wave. At the same time, they also behave like a particle. So if this concept here, it can explain most of the explanation and observation by means of the materials that we see. All right. So and this is given by the Broglie wavelength. So the Broglie says that in order to explain the duality of the electrons here, this formula must be applied. Well, I'm not teaching quantum mechanics in here, so this is just to tell you the history behind it. All right. So when we talk about wave here, here we need to understand the discovery of electrons leads to the discovery of electromagnetic wave. So we know that electromagnetic wave, there are 7 members of them. All right. Can anyone list them? Anyone? Hinky, give me one example of electromagnetic wave. You learned this in
Sound wave.
huh? Sound wave is not electromagnetic wave here. Sound wave is a longitudinal wave. So example of electromagnetic wave, EM wave, are your microwave, your gamma ray, your so-called visible light VL, your infrared IR, your ultraviolet UV, your radio wave. All right. And what else do you have there? Anyone? 7 of them. UV, IR, VL, visible light, microwave, radio wave, gamma ray. One more is what? Anybody? Yeah, start with Google search here. Anyone? Anyone? Guys, hello. Let's get something here. Casing, yes. Casing, one more. What is the last member of electromagnetic wave? Casing? Forget. You forgot. X-ray, very good. Okay, X-ray. Okay, good. Thank you. So X-ray is the 7 of them here. So this is the discovery of electrons leads to the role of electrons played by electrons here. All right. So far, any question? Anything to ask me? Are you all following? Anyone? All right. So let's go on here. So basically, what you have here, all from the beginning of the class up to now, I've been talking about electrons. All right. So electrons are very important. So let's see how do we play about with electrons here. So electrons here, we know they are behaving like wave and behaving like particle. So particle means they have momentum. Momentum means you can actually distort the direction of the electrons as they move in high speed here. All right. So we have here electrons are confined in shells, as in Form 5. Now we go to one level higher. We call them orbitals. So orbitals here is where you are supposed to find electrons. So you see, electrons are something quite minute. You can't see by naked eye. So people are interested to know how do we find electrons? Where can we find electrons? And how do I know electrons are there? There are presence of electrons around a certain region of area here, all right, or space here. So this is what we call probability, kebarangkalian. So what are the probability that if I comes to this space region, there are chances of me finding electrons. If there are chances here, how high are the chances here? So therefore, you must know where to find electrons, and this is why they define electrons here by arranging them in energy level. So the energy level is very important. So you see in your Form 5 earlier on, you only know that electrons are confined in orbital. This orbital is a certain region, certain space here. So it doesn't link to you to tell you what are the energy at this orbital here or at this shell here. And why are there only 2 electrons here? Have you ever asked the teacher why are there only 2 in the outer, in the innermost shell? Why as it goes one level higher, it can accommodate 8, and as it go to the next level, it accommodate another 8, and as it go further and further away here, how many can it accommodate? So how do we know all this about here? And therefore, this is called the electronic structures. All right. So every orbital that you see are defined by amount of energy, certain amount of energy. So if the electrons have that amount of energy, then it can stay there. If it doesn't have that amount of energy, it will not be allowed to stay into that space of the region. And this is number 1, determined by quantum number. So to classify electrons, we call them electronic construction or electronic structures here. So we put them into 4 rules here. 1, quantum number. 2, principal quantum number. 2, subsidiary quantum number. 3, magnetic quantum number. 4, spin quantum. All right. So we all know that electrons are revolving around nucleus. It is not stationary, and therefore there is a spin there. Spin means what? Spin clockwise or spin anti-clockwise. CCW or CW. So spinning refers to positive spin, negative spin. this is not so critical. The first three are very critical. So let's look at first one, principal quantum number. So the principal quantum number is n. So we define it one way to designate is KLMN quantum number. All right. Or another way to put it is that when n equals to 1, the orbital is k. When n equals to 2, orbital is L. When n equals to 3, orbital is M. All right. So this is your principal quantum number. So this is called the energy level shell, which define where the electrons are placed in. And the next level you can go in is a subsidiary, or we call that a subshell. So your subsidiary, we have SPDF. So your subshell here will be the sub level whereby the electrons can be filled up. And of course, the last one, the ML, the magnetic quantum number here. This is something to show when you subject the electron in a magnetic field. So what is the characteristic of this electron here? So your focus at the moment here will be 1 and 2, N and L, to write electronic configuration. All right. So again, I repeat, if it's n equals to 1, the shell is called K, or the orbital is called K. If it's n equals to 2, it's L. If it's 3, it's M. All right. So when the subshell here is SPDF, so every single of these level 1 of the K shell will have SPDF. Level 2 of the L shell or L orbital will have SPDF here. Now, whether they are filled up or not, it depends on the number of electrons in the element. All right. So let's look at how this is being done. Let's explain this again. So in an orbital, atomic orbital here, it is classified by 4 quantum numbers. We have seen that before: N, L, ML, and MS. All right. So basically here, the first two is very important. You can see from here, the N is called principal quantum number, which is always a positive integer. It starts from 1, 2, 3, 4 up to infinity. So the angular momentum quantum number, which is the L here, it starts from 0 up to infinity here. And this defines the shape of the orbital. That means if I have the S going back, recall back S subshell, okay, how will the shape look like? P, D, and F here. All right. So if this, we go to quantum mechanics. Let's see how do we arrange them in order. So number one, the arrangement of electrons in any atom is done in a way it is based on energy content. One, you follow by filling up the main principal quantum number, which is the N. Second, you only fill up the energy subshell, which is the S, P, D, or F, and it goes on and on here. All right. So in filling up the principal quantum number or the principal energy level, number one, you have to have electrons that are close in energy, similar in distance from the nucleus. All right. And the number that you start from for N, principal quantum number, is always 1, 2, 3, 4, and 5 up to infinity. So this is the formula, magic number. So you have your calculator in hand. So the maximum number of shells, sorry, the maximum number of electrons here when N equals to 1 is how much? Anyone? 2. Because N equals to 1, square will be 1 times 2 will be 2. So this will tell you when N equals to 1, principal quantum number 1, which is the K shell, 2 electrons. When N equals to 2, all right, principal quantum number 2, all right, the L shell, it will be 8. And the next one, 18. And the next one will be to the formula of 2 N squared. All right, that's why in your form 5, you see 2 in the innermost shell. 8 is the next one, nearest to the innermost shell. And the next one will be another 8, if I'm not mistaken, from your form 5. But here you can see it's 18. 18 means you have more subshell coming in. All right, this is only quantum number N1, 2, 3, 4, 5, 6, 7, 8. We haven't come to the subshell yet. All right, so now this is what we see here. A group of electrons in an atom here, all having the same principal quantum number, start from N equals to 1, 2, and 3. So N equals to 1 will be the lowest energy, 2 will be the highest, 3 higher, 4 will be the highest, the next highest here. All right, so again, the arrangement of electrons is based on energy. So you must always fill up from the lowest, then to the next higher, to the next higher, to the next highest here. You cannot fill up at the highest level. Just like to put it in short, if you're talking about how do you write electronic configuration, let's go back to here. How do you write electronic structure, electronic configuration? Basically, it's let's say you imagine you're in you're staying in a condominium. So in a condominium here, you have the ground floor. correct? The ground floor is where you enter, and then from there you meet a lift. So in the lift here, it brings you up to different level. Let's say there are 18 floors in the condominium here. So each of this level here is called principal quantum number. So the principal quantum number, the first, and when n equals to 1 is k, 2 will be L, M will be 3, etc., etc. So in each of the, let's say, first floor of the condominium, second floor of the condominium, third floor of the condominium here, you all have different units. Let's say in the floor you have 8 units, eight apartment there. All right. So this is called the subshell. Are you clear? So this is what it means by subshell, or the sub level whereby you can place the electron. Follow? If you're not sure, ask me. Don't be shy here. All right. Okay. So let's go to here again. The filling of level, as in you enter a condominium, you always start from the ground floor, then the first floor, second floor, third floor. So same thing here. When you fill up my electrons based on the energy content, you always start from n equals to 1, 2, 3, 4 up to the highest level. You cannot jump anyhow you like. All right. So the number of electrons. Yes.
Is it possible that you use your pointer, because when you jump the pages, it's hard to follow you. Where are you talking about?
Oh, pointer. Okay.
Yeah.
Okay, I'm here. Okay. Can you see my cursor just now? You can see the cursor?
Yeah.
Yeah, okay. All right, thank you. All right. Is this better?
Yes, thank you, miss.
Okay. So when n equals to 1, you can accommodate only 2 electrons. When n equals to 2, you can accommodate how many? 8. All right. So this is energy level at principal quantum number n equals to 1, 2, 3, 4. All right. So let's start to the next one here. Sorry. So you can have here the sub levels. We're going to the sub level, the sub shells. All right. So sub levels are found within the energy level. So the energy level here refers to n equals to 1, 2, 3, 4. So all electrons in the sub shell have the same level. So if your first floor, all right, referring to the first unit of the condominium. So you have here basically you have the same first unit in the second floor as well. You have the first unit in the third floor and first unit in the fourth floor, in the same arrangement of the location of the unit here. Same. So this is also the same for electron. In all levels of the principal quantum number, you have SPDF. Now, whether they are used or not, it depends on the number of electrons. If it's not used, that means there's not enough electrons to fill it in. All right. Again, this is based on sub-level of the energy. S is lowest, P higher, D will be higher, F will be the highest here. So it's SPDF. All right. So let's look at here. So if I talk about n equals to 1, the principal quantum number 1, which is the K shell, I will write it as 1, as into this 1 here, indicating the principal quantum number. I will have the first subshell S. Now, do I have a 1p there? Yes, you have a 1p there. Do I have a 1d there? Yes, you have a 1d there, but it's not shown here because it's not in use. Because the maximum level, when you are, the maximum number of electrons when you are n equals to 1, how many electrons can you take? 2. Remember, 2 n power of 2, you can only take 2 electrons. So in the S subshell, how many electrons do you think you can accommodate? Only 2. All right. So same, n equals to 2. All right. You will also have the n as indicated here, 2 and 2. For the subshell that you can see is also the same. You have S as well. And here you can see P coming in, the subshell. So P subshell here is the second subshell that you must have, because the lower level will be S, the higher level will be P. So when n equals to 3, you also have n equals to 3 as 3S, 3P, 3D. So do I have a 3F? Yes, you have a 3F here, but then the F is not used because count again. Now n equals to 3, go to the formula, 2 power of 2 times n power of 2 is what? Sorry, 2 times n power of 2 is when n equals to 3, that means 3 power of 2 is what? 9. 9 times 2 will be 18, correct? So you have 18 electrons at this level here. So I haven't come to the number of electrons that you can take for S, P, D, and F. I'll come to that later. So same for n equals to 4. When you have sub-level when you have the quantum principal number at 4, so all this will be 4s, 4p, 4d, 4f. What you have here, the sub-level of level 4, they will be the same as in being an S, a P, a D, and an F here. Okay, are you clear? Okay. So let's look at how we arrange them. So the energy content of every level and sub-level are arranged based on energy. So we start from here. Right. So the lowest is principal quantum number 1 is 1s. So therefore the level is lowest here. Go to next level higher, n equals to 2. All right. The lowest subshell that you have for n equals to 2 is s, so it's 2s. But the p will have a higher energy level of the s subshell, and therefore it's above it. All right. So the next one, do you have a 2p above the? Do you have a 2d above the 2p? Yes, you have a 2d, but the d is not it's not filled up because at n equals to 2. Remember, 2 n power of 2. When n equals to 2, you can take only 8 electrons. So you'll come to this later. How many electrons can go into subshell of p? How many electrons can go into subshell of s here? So when n equals to 3, all right, this is the next level of 3, n equals to 3, 3, 3. So you will have a subshell of S, P, D, and F. Remember, S subshell has the lowest energy. P is higher than S. D will be the highest. So do we have a 3F? Yes, we have a 3F here, but this is not in use because of the formulation 2n power of 2. All right. Okay. So, how many electrons are allowed in the subshell? So electrons are allowed in the subshell here, meaning that if I have 1s electron, 2s electron, 3s electron, they are having the same energy here. So the 2s electron here all have the same energy. All 2p electrons have the same energy, which is slightly higher than 2s, etc., etc. All right. So what we can see from here, let's list them one by one here. For the S subshell, you can take maximum 2. P subshell, you can take maximum 6. D subshell, you can take maximum 10. And F subshell, you can take maximum 14. These are fixed rules. All right. So it's going to be 2 for S, 6 for P, 10 for D, 14 for F here. Any question to ask me? Okay, so let's look at how do we write the electronic configuration, electronic structure or electron configuration. They are the same. So what we have here, number 1, first of all, list the subshell containing electrons. Write them in order of increasing energy. Recall back, how does it increase? As in S lowest, P the next higher, D the next higher, F the highest here. So if you're talking about subshell here, it's SPDF. If you're talking about principal quantum number, it's going to be n equals to 1 lowest, n equals to 2 next higher, n equals to 3 next higher, and n equals to 4, 5, 6 up to infinity. So the superscript here, top there, this superscript, give you the number of electrons that can fit into a certain element. Now let's look at an example. If you have your periodic table in your hand here, okay, neon, neon is a group 8, right? So group 8, the periodic table in your hand. Okay. Can you see my neon? It's 8, sorry, it's number 10. Neon is number 10. 10 electrons, correct? So it has 10 electrons, is in group 8. All right. So I want you to write down. You have a pencil in your hand here. Aluminium is 13. Number 13. Atomic number is 13. Chlorine is 17. Argon is 18. Because there are some examples later on that you can test on here. So aluminium 13, chlorine 17, argon is 18. So now we are looking at neon. Neon is 10. All right. So let's look at here again. All right. So neon, neon is number 10. So 10 electrons, meaning sorry, 10 protons. The atomic number is 10 for neon. So it means that it has 10 electrons. All right. So what you have here, we will start to write the electronic configuration as in a way from the lowest level, n equals to 1, n equals to 2, n equals to 3. Right. So at n equals to 1, the principal number of number 1, it has one subshell of S here. All right. Just now recall back, S subshell can take only 2 electrons, so therefore it's 1s2. So the next level that it goes to at quantum number 2, all right, it has a subshell of S. Again, the S subshell can only take 2 electrons, therefore it's 2s2. The next level that you go to, same quantum number 2, all right, but the P shell comes in because remember back when n equals to 2, how many electrons can you take? 2n square is going to be 2 bracket 2 square is 4 ma, 4 times 2 is 8 ma. So altogether you must take 8 electrons. But our friend here, the level of the subshell S only has taken 2. So that means there's 6 more missing. So therefore this 6 will be filled up by your P subshell. All right. So your P subshell here is going to take up the 6 electrons. You can take maximum 6. You can take less than 6 here because it depends on the filling up here. So here is neon. Neon is exactly having 10 electrons here. So can you count them? 2 plus 2 plus 6. Total number of electrons will be 10. Clear? All right. So let's look at one more order of filling example. All right. I'll give you more example later on. Don't worry. So now you can see from here. All right. See, to fill up the electrons based on the energy, number 1, it's very straightforward. You have to know the energy of the main shell plus the energy of the subshell. So what we do here is based on the number of electrons in a certain element. So bear in mind, so this is arranged from the lowest, n equals to 1. The next higher is n equals to 2. Next higher, n equals to 3. Next higher, n equals to 4. All right. Of course, this is special case because of the sequential. I'll come to that later. And n equals to 1, the subshell that it has here always start from S. S is the lowest. It will be 1s. Next one will be 2s. Next one will be 2p. So do we have a 2d? Yes, we have a 2d, but d is not used because at n equals to 2, maximum you can take is what? 8 electrons. So my S shell can already take 2. P take another 6. So 6 plus 2 is what? 8. So altogether, the 2d doesn't exist in this diagram here because it doesn't need to be there. All right. So next level that you have, your principal number will be 3. So 3s will be 2 electrons to take. Next one we have 3p. P will be taking 6 electrons. 6 plus 2 will be 8. So next one we see from here. Remember, you're supposed to have a 3d before the 4s here. So the 3d jump up because of the energy content of the S level. This is a special case here. All right. So the 3d here, d can take in how many? You recall when n equals to 3. Okay, 2n power of 2. So n equals to 3. That means 2 times 3 square is going to be 3 square is 9. 9 times 2 is 18. So our friend here in the P already had 8. Sorry, already had a 6 electron here. So the S has a 2. So 2 plus 6 is 8. So that means the D subshell can take 10. So 10 plus 6 plus 2 will be 18 when n equals to 3. All right. Now the arrangement of the 4s and 3d, and as you go higher here, it will be more complicated because the arrangement is based on energy content. It is found that the 4s has a slightly lower energy than the 3d because the 3d here is where you see the transition element coming in. All right. So therefore, we have certain rules to follow. How do I know which level comes in first? So you may be having a certain doubt on how to remember this. So this is where the simplify method comes in. Let me show you. So this is given to you in your classroom. The aid to memorize feeling of order. All right. So you don't need to crack your head here. Don't need to memorize which one comes in first here. All right. Very simple. Use your hand. Follow me. So it's going to be fill up 1s, 1s, followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s, followed by 3d, followed by 4p and 5s. Next switch to 4d, 5p, 6s, and it goes on to 4f, 5d, 6p, 7s here. So can you see it's getting more complicated here? That's why the electronic configuration where your teacher in Form 5 told you, I think you remember the teacher always tell you 2.8.1, am I right? Or 2.8.4 or 2.6. You know, that kind of electronic configuration is only suitable for explanation of bonding. So to fill up the electrons, again, I remind you, so we will fill up from the lowest level is 1s, followed by 2s. You can see my cursor move slowly. Next level higher than 2s will be 2p. Next higher level will be 3s. Followed by that is 3p. Following is 4s. Then we come to 3d, 4p, 5s. And then we come to 4d, 5p, 6s. So this is the sequential order. So in your exam, you may write this way. All right, this is how you remember. You always have the quantum number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to infinity as the n equals to the principal quantum number. Then the subshell of s, as I told you, compare that to a condominium. Every level, you have the same unit of unit 1 or unit 2 of the condo level here. So they will always have 1s, 2s, 3s, 4s, 5s, 6s. So the 1p doesn't exist because when n equals to 1, it doesn't allow the p to come in. Therefore, there's no 1p here. Hello? So next one, you can have the 2p when n equals to 2, and a 3p, and n equals to 3, and a 3d comes in as you go higher and higher level. Okay? Any question? Can we have a break of 10 minutes? We go for a break of 10 minutes here. Anyone, any question to ask me? Sorry. Oh, sorry, I didn't see your chat there. Yes, what question do you have there? Yes, Dave? Yes, you can turn on the microphone. You can turn on the microphone and ask me.
Miss,
Yes.
I would like to ask about the electron locations for the sub-levels.
Yeah, go ahead.
I don't really get the SPDF thing. Like, is it like a structure, the atomic structure thing? Multiple, is it like multiple orbits, like 2, 8, 8, something like that?
Yes, it's the same as what you learned in Form 5, except that way to write electrons doesn't explain much of the observation at higher level. So therefore, they have it arrangement of the electrons based on energy level. Because your Form 5 is only 2.8.1 or 2.8.8, those only tell you the number of electrons. It doesn't tell you the electron based on the energy content of the electrons here. So therefore, it cannot explain a lot of phenomena. And this way of representing it in a Bohr's atom is a very clear-cut electronic configuration. So this is a very good question. All right, ask me if you are not sure. You can always ask me. I'm not psychic. I can't read your mind. Anyone, just ask. All right. If it's not clear, you can ask. Raymond, does it did I answer your question?
I'm still not very clear about that.
Okay, let me explain again, because I worry someone may go off for break here because I agree to give you a break here. So let's go to the slides. Can you see my slides?
Yes, I can.
You see my slides, let's go back. All right, so you can see basically to write electronic where's the number? Okay, to write electronic configuration, this is called electronic structure. They mean the same here. All right. Wait, before that, I turn on my microphone? Can, all right. Okay. So you can still see the slide, right? Raymond, can you still see the slide there?
Yes, I can.
Okay, all right. So you can see from here. So the way we do it is that we arrange it based on energy level. So energy level is confined by 1. You must obey principal quantum number, which is n. 2, the subshell. This is only the 2 things. The other 2, the magnetic and the spin here, is extra. Those are for you to elaborate energy band later on. All right. So how do we do it? Basically, always remember, fill up based on n level. Next, subshell. So what are the subshell? Subshell means SPDF. All right. So the subshell that you have here, SPDF, is basically the small compartment or small or the sub-region that you can go in. All right. So the level here that you have here is S is lowest, F is the highest. So for every quantum number of n equals to 1, 2, 3, 4, this is quite straightforward. It's like the first floor of the condominium, second floor of the condominium, third floor of the condominium. Every floor of the condominium here, they have the same unit of let's say 1-1, 2-1, as in the one behind the number. The number behind the 1 or 2 or 3 is the unit that belongs to that level. Let's say you stay in unit of the eighth unit of the second floor here. It's going to be 2-8. Am I right? So if you're staying in the fourth unit of the fifth floor, it's going to be 5-4. So this is how you label your address in the condominium. Same thing as in here, the shells of the electrons being placed here. So we always place it based on the floor, which is the n. We call that principal quantum number. Then we go to the sub level of the subshell, which is the SPDF here. So the S level of the subshell here can only take 2 electrons. That is the condition. All right, we cannot take more. P will be 6, V will be 10, F will be 14. So how does all this come about here is because if you have more than this number located here, the electron cannot just fill in. They will go to another level because the energy content will be different. All right. So what you have here basically arrangement is you can see here. This is the arrow. So it goes up. All right, rather than coming down here. So n1, n equals to 1 is lowest, n equals to 2 is next higher, n equals to 3 will be the next higher here.
So for the 3s, it means that there are 3 electrons at the
No. 3s means what? It is the electron at the level number 3 or quantum number number 3. It fills in the s subshell. So how many electrons can the s subshell take here? 2. So this will be 3s2. But here I do not in the electrons yet because I'm talking about element. All right, so go to the same thing. So if you're talking about 2p, what do you mean by 2p? 2p means what? The electron is being placed at the level of the quantum number 2, all right, at the subshell of p, all right. It can be either 1 electron filling up, 2 electron filling up, 3 electron, or 4 or 5 or 6. Maximum is 6 for p shell, p subshell is 6 here. All right. So if you're talking about 1s, 1s means what? 1s means that electron is at the level quantum number of 1, n equals to 1. It can only go into the s subshell because at n equals to 1, remember 2n power of 2. When n equals to 1, it can only take 2 electrons. So that subshell comes from the lowest level here, which is the s subshell. So this will be 1s2. So the maximum will be 1s2. Can it be 1s1? Yes, it can be 1s1. If it's having 1 electron there. So your 1s1 will be what? Hydrogen. Your 1s2 will be the next element, helium. Are you clear now? Can you see that? I'll give you more example. Let's look at neon. So if you're talking about neon here, the electronic configuration for neon is 1s2, 2s2, 2p6. So the superscript that you see at the top here, this is called superscript. Superscript, all right, means that it indicates the number of electrons in that element. So neon is number 10. Number 10 means there are 10 electrons because there are 10 protons there. It's the neutral atom. So 10 electrons means it's going to be 6 plus 2 plus 2, 10. 10. How do I fill all these 10 electrons in the neon here? Very simple, straight to the point. I will start from n equals to 1, which is 1. The next substrate that can go in here, originally you always start from the lowest level, is S. So it's going to be 1s. How many electrons can the S subshell fill? 2. So it's going to be 1s2. So do I have a 1p2, a 1p6 there? No, because when n equals to 1, the maximum electron that can fill in that orbital is only 2, based on 2n power of 2. Are you clear? And the same thing here, 2s2 is the next higher level when n equals to 2, the principal quantum number. So basically, you have the lowest level at the quantum number of 2 is going to be S here. So it's going to be 2s. Now, how many electrons can the S subshell take? Maximum 2. Can it be S3? No, cannot. Can it be S1? Yes, can. If it's S1, it will be electrons of 1 plus 2 here will be 3. Meaning what? It's element number 3, which is your lithium. But here is neon. Neon is 10 electrons. So it will have to fill up 2 maximum. Fill up the most it can take in is 2. So therefore it's 2s2. So it only has taken 2 and 2 here, total of 4 electrons. We still short of 6 here because my friend neon is 10 electrons. So I need to know where to put my 6 electrons, the remainder of the 6. So the remainder of the 6 will go into the next higher level of the subshell, which is what? The P. After S must be P. But it will still remain at where? Quantum number 2. You cannot go to quantum number 3 because number 2 here, you still have to fill subshell P because maximum when n equals to 2, remember the formula, 2 times n power of 2 will be 2 times 4. 2 power of 2 is 4 4 times 2 is 8 So it's maximum 8 electrons. So at n equals to 2, you can take in 2 and 6 together, add up will be 6 electrons here. Sorry, add up will be together 8 electrons here. 2 plus 6 will be 8 here.
Miss,
Okay?
Miss, how does the SPD look visually? Do you mind if I present my screen? I want to show.
Do you mind what?
If I present the screen, I want to ask, is it how this looks like? Like this?
Yeah, it has shapes there. How do you present? How do you present?
You can see that.
Oh, no. This is your Form 5 level. You
So
see,
it's,
yeah.
so it's different.
Yeah, no, this is your Form 5 level. You see, your okay, attachment. Go back to the diagram that you've shown here.
Hold on.
Okay, all right, guys, are you here? Everyone is here. So you can see this is he wrote as this as P, D, and SPDF. This doesn't show me my subshell. This only show me my principal quantum number of K shell, L shell, M shell. Remember K is what? N equals to 1 L is what? N equals to 2 N equals to 3 what? Your S is your KLM. So this is your Form 5 method here. It doesn't tell me, oh, why are there 2 electrons at the n equals to 1, which is the K shell here? That's why in here you find that it is only 2 electrons because the S subshell must be there, and S can take how many? Only 2.
So it's talking about inside it.
It's talking about more advanced level of electronic configuration. That means how you arrange electrons based on the energy content. This is only Form 5 level. Form 5 level only can explain up to here based on the bonding. That means you know that electrons at the outermost here is called valence electron. So those valence electrons are the ones used for bonding. So in this diagram here, you can explain well, but you cannot explain other phenomena which is more complicated. So therefore, you use the SPDF configuration, electronic configuration here.
So if the SPDF, does it have a diagram to explain it?
Oh, the SPDF has a certain shapes here. So the SPDF is actually subshell. So in this diagram, your Form 5, can you see the subshell? You cannot see subshell, correct? You can only see orbital 1, orbital 2, orbital 3, which is actually n equals to 1, n equals to 2, n equals to 3. These are not the subshell. So actually, if you go to n equals to 2, the L shell, you can see there is 2s there and there's 2p there, but you cannot draw onto here. Am I right? Why?
So it's talking about
this one dimension. Yeah.
Okay,
This is one dimension. It's not energy content. So this is only telling me that is how I feel my electron based on one dimension layout here. So I cannot illustrate more if I want to explain. So the best is to use energy because electrons are moving. When they move here, they have energy, potential energy and kinetic energy. So the moment you can capture electrons, because it's too small, you can't see by naked eye. So therefore, we have to use other means to trace electron, other means to discover electron, to track down the electrons here. And this is how we use energy.
All right, I get it.
All right. Are you clear?
Thank you, Miss.
Thank you. What next one? All right. So is everyone back? Ask don't be shy. Okay. So let's look at here. Order of filling. So far, I know this is quite new to you because it's energy content here. So if I give you a couple of examples, you should be able to get it better here. So again, remind yourself, n equals to 1, always starting point. Then next one is 2, 3, 4, and 5, and 6 here. So in each of the level here of the quantum number, it has a subshell, sub-level. We always start from the lowest is S, P, D, and F here. So you don't see F here. F is complicated because it goes to the lanthanides and the actinides here. Right? So the D is where you see the transition element in the periodic table. All right. So now how do you write? Let's look at more illustration. So if I have hydrogen, remember hydrogen is element number 1. H is the symbol, so it's going to be 1s1. If it's the next one, helium, 1s2. What does it mean by 1s2? It means electron that is in helium is how many? 2. Why 2? Because helium is what? Atom number 2 ma. Atom number 2 means what? The proton number is 2. It's neutral ma. So 2 electron and 2 proton, they are neutral. Correct? So we were talking about your arrangement of electrons, so we don't touch proton at all here. So all the while we're talking about electrons here. Next one, what's the next element? Lithium. So in your form 5, your teacher asked you to remember 20 elements of the periodic table, correct? So we have hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, then we have the fluorine, neon, etc., etc. So you have to memorize by heart. By now you should have forgotten. So if you talk about lithium, lithium is number 3, ma. So lithium number 3 here is going to be filling up 1s2. Subshell S can take in only 2, correct? So this is already fulfilled, finished, completed, cannot fit in anymore, correct? So can it go to a 1p6? No, there's no p there in the n equals to 1. So it has to go to n equals to 2. So n equals to 2 is what? The next sub level that it start from, always the lowest is S level. All right, so S can take in how many? 2. But here you only take 1. Why? Because my friend, the helium is lithium is number 3, ma. So lithium number 3, it needs only 3 electrons because the proton number is 3. So what we have here already got 2. The superscript means the number of electrons filled up, so only have 2. So only short of what? 1 more, become 3, ma. So this is 1. So it's going to be 2 plus 1, 3. So if you see 1s2, 2s1, this is lithium. All right, are you clear? So next one, carbon. Now carbon is how many? Carbon is going to be 6. Carbon is number 6, if you recall back. 6 means what? Atomic number 6, proton number 6, electron 6. So 6, how do I fill up? So it's going to be 1s2, 2s2, 2p2. Now 1s2 is what? It starts from the lowest level of n. All right, the subshell lowest at n equals to 1 is s, ma. So the 2 electrons that can fit in the s subshell will be only 2. All right, next it goes to the next higher quantum number, which is 2. The lowest subshell will be s. At the subshell level of S, it can only take 2 electrons. So therefore, it's 2s2. Now, how many electrons are here? 2 plus 2. All right, 2 plus 2 means what? 4. So how many is short? It's still short of 6. 6 is still short of 2 because carbon has 6 electrons. So you need to put in another 2 more where you have to go to the p level. So the p level still goes into the quantum number of number 2. So it's 2p2. So it's all together, if you look at the number of electrons, it's going to be 2, 2, 2. Yes. Okay? Is it clear? Hello? Yes. Someone speaking there? Yeah, can you repeat your question? Anyone speaking there? Yes, ping. Ping, what do you mean by affirmative here? Yeah. Can I go on? All right. So let's go on to here. Sulfur, S. Sulfur. Now, anyone coming? Sulfur is number what? Element number what? 16. 16. 16 means what? Proton number is 16. Electron number will be 16. So let's look at how we fill up. So we fill up from n equals to 1. The subshell when n equals to 1 is always start from S. So in the S subshell, you can only take 2. All right. After that, can it go to 1p? 6? No, there's no p subshell in the n equals to 1 quantum number. So it has to go to the next quantum number 2. All right. The lowest level of subshell will be S, and therefore it will go to 2s. How many electrons can fill up in the quantum number of number 2? How many electrons can fill up in the subshell of S? It's going to be 2. So after that, you have same subshell remainder in the quantum number 2, which is the P. All right, P can take in how many electron? 6 electrons here. So what we have here, 6 electrons is going to be fill up the P subshell. Now altogether, how many have we used? 2 plus 2 plus 6, 10. So we're still short of what? Sulfur is 16, we're still short of 6 here. So we have to go to the next level. Next level, can I go to 3, can I go to 2D? Is there a 2D there? No, there's no 2D because why? At n equals to 2, maximum you can take in how many? 8 electrons. How do I know 8? It's 2 and 6. 2 and 6 means what? Already fill up 8 electrons here when n equals to 2 based on the formula 2n power of 2. So when n equals to 3, the next level, again start from the lowest subshell is S. So S can take how many? 2 electrons. So 2 electrons here. Does it fulfill my sulfur, which is 716? No, I still have what? 2 plus 2 plus 6 plus 2, 12. I still short of 4. So let's look at here. Next one you can go to is n equals to 3, quantum number. The subshell that you can go after your S subshell at level 3 will be P. All right, P can take how many? Maximum 6 electrons. But here I only need to fill up only up to 4 because when I fill up 4, I already have 4 plus 2 plus 6 plus 2 plus 2. How much? 16, which is my sulfur. So altogether, I only use the orbital, the subshell of P, 4 electrons in it. That means I have 2 more empty space to fill up if I want to add electrons. All right, so this is your electronic configuration. So for sulfur, it's 1s2, 2s2, 2p6, 3s2, 3p4. Right? So let's look at more example. Okay, in order to write electronic configuration here, first we have to find an element in the periodic table. Periodic table in your hand, soft copy. Use the order of filling. Always start from level of subshell S. Go to the next level is P. Next level is D. Next level is F here. So can you see when you fill up the electrons in the D level here, we are actually involving the transition element. And just now I told you, very rare you will get the F subshells will be filled up here because the lanthanides, the actinides will be all there. So most likely you will use the S and P subshell, which is always your group 1 up to the group 8 that you have exposed to in your Form 5 here. All right. So let's check. All right. Potassium. Now indicate if the configuration given to you, if it's wrong, it's 2. If it's correct, it's 1. So give explanation why is it wrong or right here. So let's have someone random. Okay, let's call some names here. All right. So we have Qingyi. Gan Qingyi, are you here? Gan Qingyi?
Yes.
Yes, Qingyi.
Yes,
A. Correct or wrong? Correct or wrong? For A, we have 1s2, 2s2, 2p6, 3s1. Is this way of writing electronic configuration? Let's say for X element, is this correct or wrong? 1s2, 2s2, 2p6, 3s1. So let's check that. I got you. So is this in the right order? Starting from the lowest n number of quantum number? Yes, 1, 2, and 3. All right. So let's look at the subshell. Is this starting from the lowest subshell? Always S. When n equals to 1, you can only have one subshell, which is the S here. You cannot take in P. All right. So at here 2s subshell. All right, good. All right, it start to the next level 2p. Correct. So when at 3, it will start from the subshell of s. All right, fine. So let's look at here. You can fill up at 1s quantum number n equals to 1, 2 electron. Maximum for the subshell of s here, yes, 2. So for s quantum number 2, is it 2? Yes. Quantum number 2, the p subshell, is it 6? Yes. So quantum number 3, s subshell, is it 1? Qingyi, 1 or 2? Hello, Qingyi, Mr. Gan? Yes, it can take in 2, but here is 1. Is it wrong?
Yes, wrong.
It's not wrong, it's right. Because this can fit in maximum 2, but you only need to take in 1. That means what element is this? You count for me. 1 plus 6, 7. 7 plus 2, 9. 9 plus 2, 11. 11 is what element? Sodium. So this is correct.
Miss, your question is asking for potassium.
Yeah, I'm talking, it's asking for potassium, correct. But this configuration is correct, but it is for what? Sodium. So is this potassium? No. Okay, good. You get it? Follow? So is A correct? Incorrect. I'm talking about this configuration. Is this written correctly? Yes, it's written correctly here, but then it doesn't answer to the question because it's asking for potassium. It's not asking for sodium. All right, so let's look at B. So B, let's check it out here. By now you should be able to know. You always start from 1s, 2s, 2p, 3s, 3p. This sequential is correct. Right. So let's look at how many electrons are there. This superscript here will tell you the number of electrons filling up each of the quantum number and the subshell. So this is 2 plus 2 plus 4. Sorry, 2 plus 2 is 4. Plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. So is this potassium? No. 18 means what? 18 is element number 18 is going to be argon. So this is not potassium. So what's the answer? A, B, C, D, E. Qingyi, what do you think is the best answer?
E.
Okay. Now mine. All right. Let's look at here. Qingyi, I got you. Let's look at C. So it's 1s correct, 2s correct, 2p, 3s, 3p, 4s. Yes, the sequential, the order of energy content is correct. So let's look at how many electrons are there. 2 plus 2, 4, plus 6, 10, 12, 12 plus 2, 18, 19. So this is element number 19. So element number 19 is going to be potassium based on the periodic table. All right. So is this order correct? In filling up of the electron based on energy content? Yes. All right. So next one, if you look at D, so 1s2, 1s is correct. Then you jump to 2p. Is this correct order of sequential of energy content? No, it missed out my 2s subshell. So you cannot jump from 1s omitting the 2s and then jump to 2p here. So my 2s is missing. And then it tells you here p, how many electrons you can fill in for the subshell of p? 6 to the maximum. But here it says to you 8. So this is not fulfilling the order here. So this arrangement of the electronic configuration is totally wrong, and it is not correct. And anyway, does it represent potassium? No, it doesn't represent potassium. Potassium is supposed to have what? Potassium is supposed to be 19 electrons. So if you look at here, 1 plus 6, 7, 7 plus 2, 9, 9 plus so-called 10, which is going to be 19. So the answer will be C. So let's look at E. Let's check out. Now, can you see, is the order for sequential filling of electrons based on energy, is it correct? So it's 1s, 2s, 2p, 3s, 3p. Yes, the order is correct in the energy content. But the filling up of electron, let's say, S subshell take 2, S subshell can take 2, P subshell can take 6, all right, fine. This S subshell can take another 2, but the P subshell in here cannot take 7. It can maximum take only 6. So this is 7. That means the way to write the configuration is also wrong. Even though you add up to how many? Can you count? 2 plus 2 plus 6 is 10. 10 plus 2 plus 7 is 19. Even though this may have 19 electrons here, the superscript tells you 19 electrons, but the electronic configuration that you have here doesn't represent potassium because the order that you fill up the electron for the P subshell, maximum you can take is only 6. It's not 7. So what do I do with the extra 1 electron? I have to go to the next level. The next level is what? 4, because after 3 is going to be n equals to 4. And at the 4 quantum number, what's the lowest subshell? S. Are you clear, students? Can all right. So basically, these are the answer. The answer is C. All right. So now let's look at this example here. So use the periodic table. Hopefully you have it in your hand, soft copy. Write the complete configuration for each of them. Just now I told you to write it down in your paper here. So chlorine we have 17 electrons. Aluminium have 13. Write down on your piece of paper if you have any. 17 electrons for chlorine because the proton number is 17. Atomic number for aluminium is 13. Argon is 18 here. So what do you think is the right answer? So we shall start from anyone? All right. So let's start from here. So we should write as in a 1s2, 2s2, 2p6, 3s2, 3p5. So do I write 1s2, 1p6? No, I don't, because at n equals to 1, the p subshell cannot come in. When n equals to 1, based on the formula 2n squared, maximum at n equals to 1, it can only take 2 electrons. So that 2 electrons will fill up to where? The s subshell. How many electrons can the s subshell fill up? 2. All right. So next one, here is the highest level after 1 is going to be 2. The lowest subshell will be s. The next higher level of the subshell will be p. So p can take in how many electrons? 6. All right. So what you have here, add up all the electrons at the superscript. This is called superscript. All right. This superscript tells you the number indicating the number of electrons available for filling up. So here is 2 plus 2 plus 6, 10. 10 plus 2 plus 5, 17. So electron number of total 17 here represent what? Chlorine. So is this way of configuration, when you write it down, is it correct? Yes, the order is correct. Based on energy content, based on quantum number, based on filling up of the number of electron for every subshell is fulfilled. Follow? So for aluminium, same. 1s2, 2s2, aluminium is 13. So 2p6, 3s2, 3p1. So how many electrons are there in the aluminium? Let's count. 2 superscript plus 2 plus 6, 10 plus 2 plus 1, 13. So 13 electron represent what element? Aluminium. Because why? Aluminium is neutral, as in having 13 proton, it must have 13 electrons. All right. So can you put your 1 here for the p subshell electron, put into s3 here? No, you can't, because 3s3 does not exist. The 3s3 is wrong. You can only take in for subshell of s 2 electron maximum. All right, argon the same, 1s2, 2s2, 2p6, 3s2, 3p6 here. So you can see from here, now is the order correct? Yes, it comes from n equals to 1, n equals to 2, n equals to 3. All right, is the subshell correct? When n equals to 1, I have only one subshell, which is s. When n equals to 2, I have 2 subshell, which is s and p. Can I have 2d? I can't. Because why? When n is equals to 2, you can only take in a maximum of what? 8 electrons based on 2n power of 2. All right. So is this 8 electrons fulfilled? Yes. 6 electrons come from the p shell, subshell, and 2 electrons come from the subshell of s here. And from here, I have a 3, n equals to 3. So n equals to 3, do I have a 3d? Yes, I have a 3d, but do I need to use them? No, because argon is only number 18. So altogether, I have here is 2 plus 2 plus 6 is 10. 10 plus 2 plus 6 is 18. Is this argon? Yes, argon is 18. So it's already free up. So my 3d is originally there, but it doesn't show in here because I'm not using that orbital here. That subshell as well here. All right. So let's recap. Let's have a fast quiz here. So number of electrons in the p orbital. Anyone? Anyone? Number of electrons in a p orbital?
6.
There's no 6 answer here. So you can see here. So the p orbitals, the subshell is what I've been telling you. All right. The orbitals are the boxes of the subshells that you can fill in the electrons here. So in here, the subshell p orbitals here you can fill up is actually 6 electrons. So what you have here, each of the subshell here, they have small boxes. The boxes here, they are actually filling up. The maximum here is only 2 electrons per box. So in here, we have altogether 3 boxes in the P subshell. So therefore, each box can take in 2 electrons. 3 times 2 will be 6 electrons here. All right. So number of orbitals in the P subshell is actually 3. All right. Number of electrons in each of the P orbital is actually either 1 or 2 electrons. All right. But the number of total electrons in the P subshell will be altogether 6 here. So the number of orbitals in the 4D subshell is how many? Remember 4D just now I told you D can take in how many? 10 electrons. So 10 electrons, it has 5 boxes, 5 compartments. All right. So these 5 compartments, each of them will take in only maximum 2 electrons. So 5 times 2 altogether will be 10. So altogether in here, the number of orbitals in the subshell of D will be 5 only. But the number of electrons that you can take in is 10. So the number of electron maximum in a 3D subshell will be what? 10 electrons here. So you must be able to differentiate 1, quantum number, 2, subshell, 3, orbitals. All right?
Roger, can you repeat this one again?
Come again?
Can you repeat this one again?
Okay, fine. So you can see from here, so it's asking you P orbital and P subshell. P subshell is what I always tell you, as in the subshell, you can take in 6 electrons, correct? Of P. In the subshell of S, you can take in 2 electrons. In the subshell of D, you can take in 10 electrons here. So each of these subshell here, it can break into smaller parts. We call that orbital. All right, the orbitals here is the little boxes in the P shell here. So this P shell has 3 boxes. So each of the 3 boxes here can take in 2 electrons. So 2 times 3 is 6 electrons altogether. So here is asking you onto a smaller level of an orbital into the subshell of P, and how many electrons are they able to fill up here?
Miss, how do we know how many electron is in one orbital? Like P orbital, how many electron? D orbital, how many electron? How do we know that?
Good question. All right. So in the P subshell, maximum is 6 electron. So 6 electron here, the P subshell has 3 orbitals, 3 little small boxes.
Mm-hmm.
Of the box here, there are 3. They are, in the P subshell, there are 3 boxes here. So 3 boxes means that each of the boxes can take in 2 only. Maximum is 2 electrons. So in each box, how many electrons altogether? 6.
2. Yeah, 6.
No. 6. So for the P subshell, how many electrons can you take? Maximum 6.
Okay.
All right. So in the D subshell, maximum is 10 electrons. So how many boxes are there? For each box, you can only take 2. So maximum boxes is 5.
Okay.
So the orbitals in the subshell is 5 for D. Orbitals in the P shell is going to be 3. But each of the orbital in the subshell can take in only 2.
Okay.
All right. Can?
Each orbital can take in, each subshell can take in 2 electrons.
No, each subshell, subshell is only S, P, D, and F only.
Okay.
Correct? So S can take in 2, So S subshell is 1 little box. In that 1 little box, how many electrons can you fill up?
2.
Yes, correct. So in the P subshell, we know they are able to take in 6 electrons. 6 electrons.
Okay.
How many more boxes do we need to take up the 6 electrons there?
2.
Each
3.
box will take in 2 electrons,
Yeah, so 3 boxes.
there will be 3 orbitals, correct. There will be 3 small boxes. The small boxes is what we call the orbital there. Are you clear?
Yeah.
So therefore, you see the number of electrons in any orbital, whether you are talking about P orbital, D orbital, or S orbital, how many electrons can you fit in? Maximum is only 2.
Okay.
All right. But in the P subshell, how many boxes are there? We know
3.
that P subshell can take 6 electrons, so they must have 3 boxes so that each box can take in 2 electrons. 3 of the boxes, each one has 2 electrons, so all together add up to 6 electrons here. Follow?
Okay. Yes.
Same thing. For D shell, D has 10 electrons to take in. So each of the small little boxes, there are 5 boxes. Why 5? Because 5 in each of the small boxes can take in 2. 5 times 2 will be 10 boxes there. 10 electrons here. Follow what?
Yes.
This is a class. Don't worry. This is to test you only. All right. So let's look at it again now. Can you see now? This is a higher level, no longer in your Form 5 level where you draw those circles here. So can you see? We start from energy content, lowest to highest. You see the arrow goes up here. Always start from the lowest here, 1s. This is 1 orbital. You can see actually it's 1 orbital here. All right, or one box that I say to you just now. One box can take how many electrons? Maximum 2. All right, so next level is n equals to 2, correct? What's the lowest subshell? S. When we come to n equals to 2, can I have the subshell of P coming in? Yes, I can. All right, can I have the 2D? Yes, I can. But 2D is not shown here. Why? Because when n equals to 2, it must fulfill the order of 2n power of 2, ma. 2n power of 2 is what? 8 electrons only, ma. Correct? So 8 electrons only here, so that means I cannot use up to the subshell of P. I cannot use subshell of D. D must not be shown here. It's redundant. All right. So let's look at here. Can you see this little line here? This line means what? It's the place where you put in electron, ma. Correct? So this line means I can put in 2 electrons here because S subshell can take in how many? 2. Same as here. This is the subshell of S. How many electrons can it take in? 2. Right? So in the P subshell here, how many orbitals are there? Just now the question asked you, right? There are actually 3 boxes, 3 orbitals here. So each orbital here, this is 1 orbital, this is 1 little box here. How many electrons can it take? 2. So altogether 2, 2, 2, and none. So it's going to be, maximum is going to be what? 2p, 6. Maximum can take in only 6. Can I have 2p5? Yes, I can have 2p5 because it's still have one more space empty, ma. Maximum it can fill up is 6, ma. Can I have 2p4? Yes, I can. Can I have 2p2? Yes, I can. Can I have 2p1? Yes, I can. Can I have 2p0? Yes, I can. 2p0 means what? That element become an ion because the electron is taken away from the p orbital already. And this happened at where? L shell. What is L shell? N equals to 2. Everyone, any question? Ask me. Don't stop. Don't keep quiet. All right. So next element. Can you see n equals to 3, n equals to 4, n equals to 5? The complication comes in when n higher and higher and higher. So you can see the energy skip. It's no longer following the order. This doesn't always mean that after my 3p, I must have my 3d. The d is higher level energy content than the 4s here. So it must follow the energy level content here. Even though we know that the 4 comes in should be higher level than the 3D here, but this is not the way because there are rules to obey. Are you following me? So this is called the M shell and the K shell and the L shell and the N shell here based on what? Principal quantum number N equals to 1, 2, 3, 4. Follow? So can you see from here? Just now the question asked you in the D subshell, how many orbitals are there? 5. Each of the orbital can take in how many electrons? 2. So 2, 2, 2, 2, 2, altogether 10. Can I use up all the 10 spaces here? Yes, I can. Can I not use up all the 10 spaces here? Yes, I also can because sometimes when the element you fill up one by one by means of the electron, you don't have to fill them out all because they do not have that number of electrons to fulfill. Is that clear? All right. So let's look at how we write electronic configuration. So first thing, completely fill up all your S orbital subshell. Completely fill all your P subshell here. No matter what level you are here, whether you're at quantum number number 1, quantum number 2, quantum number 3, quantum number 4. All right. And these are all neutral. That's why it's stable. All right. They're unreactive. That's why they're stable neutral. They haven't become ion of a positive or negative yet. All right, let's confirm. Helium is Z, atomic number is 2, so it's 1s2. Agree? Can I write 1p 0? I don't need 2. There's no p subshell exists in helium. So neon is 10. Atomic number is 10. 10 electrons here. So can you see? First thing you check how many electrons are there in neon. So look at the surface split. The number at the top there. 2 plus 2 plus 6, 10. All right. Is the order of filling up correct? Let's say 1. N equals to 1, N equals to 2, N equals to 3. I don't need to go to N equals to 3 because it's only 10 electron. All right. So I only use up to N equals to 2. So let's look at my subshell. S and P. Are they in order? Yes. When I say in order means are they arranged in energy level? All right. So your argon, 18. So let's look at here. It's 1s2, 2s2, 2p6, 3s2, 3p6 here. How many electrons are together? Look at the superscript. 2 plus 2 plus 6 plus 2 plus 6. 18. So you look at your krypton. Krypton is 36. Krypton is one of the inert gases here. Atomic number 36 electrons. So therefore, you see the more electrons coming in, the more complication of the arrangement of the electronic configuration here. So you can see from here, let's count total of electrons. Let's see if tally 2 plus 2 plus 6, 10, 2, 6, 18, plus here 10, 28, 28 plus 2, 30, 30 plus 6, 36 here. Are the electrons correct? Yes, the number of electrons are correct, but are the order in sequential energy content here? Let's check out. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. All right, you can see my 3d here is filled up, and then I have my 4s2, 4p6 here. So can you see it goes to the level of quantum number 4 here. So can I write my 4s2 here and then bring my 3d10 here? Yes, you should do that. That should be the way here. So this is only to tell you arrangement of electrons on energy content, but in actual presentation here, this is not the right way because the energy differs when it comes to a D and 4s here. When it comes to 3D and 4s, there's slight difference in the energy content. And going back to that, just to recap, to here. Correct, very good. Fan Ying, yes, correct. S orbital has, S structure has 1 orbital, P has 3 orbital, and D got 5 orbital. And each orbital can fit in 2 electrons, correct? Yes, that's right. Correct, absolutely right here. So let's go back to where I want to tell you. I know you've been very patient with me here. Wait, where am I? Let's go back to here. Let's check back. Okay, let's go back to here. Can you see this screen here? Can? So let's go back. Order of filling up of the electrons based on energy. I look at my cursor, my pointer. 1s. You see how I move 2s, 2p, 3s, 3p, 4s. Just now you see the krypton, it was 3D coming in, right? That's not the right way. It's not wrong, but just want to tell you there are ways to do it here because in actual case when you write it, you follow the energy content. So this is 4s followed by 3D, 4p, 5s. You see, you don't go to 4D, you skip and then you come to 5s because 5s energy is lower than the 4D. So the 4D is higher, then you have the 5p, the 6s, and it goes on, etc., etc. So again, I repeat. So it's 1s. You use your hand, move up and down. 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc., etc. You just follow the order of the arrow. You will not get it wrong in all ways here. This is the technique. Follow? Okay? So we shall stop here. Where am I now? I'm at the slide number 40. We shall stop here and continue on Thursday here. So any question to ask me? Oh, F can fill in how many? Very good. How many can you fill in? 14. Very good. How many boxes are there? 7. How many boxes? When I say boxes means what? How many orbitals are there? 7 orbitals. Each orbital can fill how many electrons? Maximum 2. Is that clear? Hello, anyone?
Yes,
So yeah, mechanical students, are you all right?
Yes,
You
clear.
can ask me again. So thank you for staying up to 2 hours here. So I shall see you on the Thursday again here. So have a lovely lunch break. Enjoy your day.
Miss, are you going now?
No, I'm still here. You can ask me. Yes.
How to say? Just now, is it possible for you to like record your session and then you repost it onto Google Classroom?
Oh God, I didn't record.
No, it's okay, it's okay. I just
No, I
saying
didn't
for
record
next
this
few
one.
lesson, for next few lessons.
Sorry,
Yeah.
come again.
I would like you to is it possible
Yeah, this one I didn't record.
to replay it later?
No,
Yeah, it's okay, but for the next few lessons.
Yeah. This one I didn't record. Okay, I'll bear that in mind. Thank you. Anything else?
Because sometimes you're going too fast, then you jump and then we get confused. Yeah.
All right. Okay, noted. Anything else? So to record, record video. All right. So okay.